Actually, I'm going to work with roughly half of the audience. Well, the goal is roughly this. So we've had a lot of presentations, discussions about approximation complexity of various problems and so on. And well, if you think about it, most of those, or many at least, of those things, well, either concern sort of, well, fairly narrow problems, like, for instance, two-spin model and related things, or a little bit disorganized in a sense. So, well, we can talk about this or about that, and so on. So the overall goal here is to sort of think a little bit about more systematic way of studying these things, and what can we see in general in this area of approximation complexity of partition functions in CSP. So a little bit about notation. Well, many examples I'm going to use are actually CSPs, which means that they use, say, relations rather than functions. But every time we see a relation, we actually think about it as a function. So it will be more convenient and uniform for us. So every relation is actually a zero-one function. And so we usually, well, every time I won't be talking about relations, it's always will be functions. Okay, and well, I will assume that functions are non-negative and so on. Okay, so just agree on notation and terminology. Well, we are talking about weighted constraint problems, or which is the same thing, partition functions. Well, they will be parameterized by constraint languages. So what is a constraint language? Here for us, the constraint language will be just any set of functions of the type we talked about. Then the problem of computing the partition function or counting CSP over this language, okay, this number CSP of gamma. Well, again, the instance is as usual, right? So we have a bunch of variables. Well, we impose all these functions on some of those variables, and we multiply them. So, for instance, if we take a specific some mapping from the set of variables to our domain, then the weight of this mapping, well, we compute as, well, in the natural way. We take the value of variables, apply functions to them, and multiply everything together. Okay, what we want to know is, well, the partition function, the sum of the weights of all mappings. Okay, this is what we do, have been doing, well, the past 3 days. So it's more or less the same problem. Just the main notation we have to notice here is this. Okay, well, I will use several running examples. So again, to introduce notation, well, we have seen almost all of them already. So just to introduce notation. Well, say counting, satisfying assignments of three such formulas. It is equivalent to our counting CSP of some constraint language, where this constraint language actually consists of the 4 0-1 functions that encode the four possible three clauses. Right? What?
Two are sufficient.
Okay. Well, we don't have to be very sort of mean in that sense. Well, 4 is okay. Right. Okay, well, another example is this counting solutions of systems of linear equations over finite field F. Well, if we do it sort of in a formal way, this is the same as counting CSP of, say, gamma sub F, where this constraint language is just the set of all 0-1 functions that distinguish a solution to the system of an equation from a non-solution. So in this case, we have only 4 functions. In this case, we have infinitely many. Well, if we want to be kind of more mean, as Mickey wants to be, well, we can sort of reduce here everything to equations over 3 variables and so on and so on. But I don't want to do it here. It's not very important right now. Also, I will discuss such issues a little later. Well, graph homomorphisms is a very rich source of various examples. So, well, we want to count homomorphisms to a fixed graph H, and clearly this is counting CSP. Constraint language is just the edge relation of the graph, nothing else but that. And again, well, a few examples we have seen so far. K-coloring homomorphisms into a clique. So it's just, in this case, this is just a disequality relation. Counting independent sets should probably be undirected at this edge. So in the counting independent set, well, forget about arrow. Okay, this is okay. Again, just counting homomorphisms into this graph, and if you take the edge relation, well, this is what you get. Okay, bipartite independent set, slightly more involved. So we're talking about bipartite graphs. We're mapping them here. Then the preimages of these two vertices clearly form an independent set. Okay, in this case, preimages of this vertex form an independent set. Okay, what else? Various examples from the two-spin model. If A is a matrix, 2 by 2, very small, well, this matrix defines a function in a very natural way. The function, it's defined on 0 and 1, right? Just on binary function defined on 0, 1. So Fij is just the entry of the matrix. So we may look at the matrix as the operation table of our function. Various special cases like Ising, for instance, of this parameter gamma. Right? In this case, our matrix looks like that. Two-spin of alpha, beta, well, again, very important special case. Well, our matrix looks like this. Well, if we want to generalize, we can always do that. Also, I'm not going to use this specific example, but if you want to generalize to many spins or larger domains, well, we can just do the same as before, and we get something similar to Potts model, or generalizations of the Potts model. Okay, so I'm going to use all those examples, but okay.
Perhaps a general question, right? In the set that A is finite, fixed finite set for you.
Yeah.
So, for the Potts model, for instance, life would get presumably easier if A was also real. So if the spin were real numbers. So I think it's true that if they're integers and they're very large integers,
right,
large range, then
right,
the partition function can become easy to compute. Isn't it? Or but somehow that's not the case you want.
I don't think. Well, so we have what? Our functions look like this, right? So we take this small domain and map to real. So the values are real,
Right.
and they can be large. And then, but in what sense? What do you mean by saying that life would be easier?
Spins or any real numbers.
So a spin is any real number.
And, you take the e to the minus square of these things or whatever.
I see. Well,
life becomes easier, but I don't know whether that's not the kind of thing that you all deal with.
right. Well, how do you find partition function? Probably some sort of integration then.
Yeah, some sort of.
It's no. Well, I don't.
Future work to me.
Maybe future work. I don't know. No, that's yeah. Well, that's a kind of. It makes sense definitely.
It's like a volume, right? And because the integration of this constraint becomes like a volume, which
yes,
for which the complexity,
Yeah.
is a different matter.
Is a different matter, yeah.
so it is different thing, but but it makes sense. Yeah. Okay. Anyway, so maybe later, next workshop or something. Okay, so these are examples I'm going to use freely, but nevertheless, I will try to remind every time I need one of them. So, approximation complexity. Clearly, the complexity of this problem depends on gamma, and we know some examples of that, say, counting the number of solutions of systems of linear equations, number of homomorphisms in a Dyer-Greenhill graph that we might know by now what they are. Say, CSP of any gamma where gamma consists of sort of very highly decomposable functions that can be represented as product of unary functions. Variables are very independent. So all those things are easy to count exactly. So, okay, forget about them. If we take slightly more interesting functions, like, for instance, Ising of Fourier Ising, well, this is Fourier Ising when gamma is greater than 1, or 2 spin of alpha beta, where alpha and beta belong to some interesting region. Well, then we know that there is an F-press, although we cannot count exactly. Well, in some cases, like, well, 3-sat, k-sat, more general, well, we have very difficult problem. They are number sat hard, for example. Right. This means the complement of the interesting region. Which is, of course, another interesting region. Right. Well, these are sort of what we can expect, more or less. Easy, slightly more difficult, very difficult. Well, as we've heard, there are some odd cases. Well, for instance, counting the number of independent sets in bipartite graphs. It's probably doesn't belong to one of those. Or, for instance, well, this is equivalently, the number of CSP of this language which consists of one function which is implication. It's the matrix 1, 1, 0, 1. Right. It just encodes implication. They are equivalent, and no surprise they are bis-equivalent. But there are other odd things, even odd things. For instance, counting the number of Q colorings of bipartite graphs. It's absolutely unclear what it is, so it's something else. But what exactly, nobody knows. So there are various things, and again, as was observed before, in terms of approximation complexity, the landscape is a lot more complicated than for exact counting. Okay, so the general goal is quite ambitious. Well, it's the goal of the whole workshop, of course. So we want to classify the complexity of these problems for all gamma, for all constraint languages, which is probably looks like some future work. But what does it mean classify? So let's see, that's actually the main motivation of what I'm going to talk about. So ideally, we would like to say we have two languages and they do have different complexities. Their complexity is different. But unfortunately, this is a little bit too much to ask, right? We need to separate a lot of complexity classes. So if you want to solve that problem on the previous slide in this sense, well, as a warm-up, you probably can prove that P doesn't equal NP. Then sort of turn to serious business like this. Okay, well, we may try to relax it a little bit. Well, we may try to prove it under some assumption. And indeed, F-press and bis-hard and sat-hard, counting sat-hard, well, can be separated under assumptions that say NP doesn't equal RP or something like this. But even that doesn't seem to quite suffice because, for instance, that BIS is not F-pressable by itself looks like an assumption, which is fairly feasible, but nevertheless. So going this way, we may get more and more various assumptions, and where to stop is not quite clear. Well, okay, weakening the goal even further, we may look for some kind of evidence that things are different. Well, what can be evidence? Say, one source of such evidence is, of course, logic. Well, descriptive complexity does exactly that. And we know, for instance, that some good complexity classes can be described as expressible in some logic. For instance, NP or number P can be expressed as problems, can be characterized as problems expressible in the existential second-order logic, or counting models or formulas in such logic. Well, BIS is, corresponds to some convoluted logic with horrible abbreviation. I don't dare to read. This one, I actually defined it in one of my talks. So I'm done with my duties about definitions. I'm not going to define it here. Okay. This is interesting thing. If you if you have this exact polynomial problems solvable exactly in polynomial time, what is the logic for them? And actually, in logic itself, a very closely related question was of great interest. So people were trying to express P by a logic, the class of polynomial time solvable problems. And one of the difficult things is how do you express in logical terms the rank of the matrix, of a matrix. That was very difficult somehow. So it was quite elusive. And for counting problems solvable in polynomial time, rank is very important. So that's exactly the missing piece in some sense, which was missing from both decision and counting problems. So what was the attempt to resolve that? Well, people started to introduce more logic operations, like a rank operator. That would, you give it a matrix and it would return you the rank of the matrix. Okay, it's solvable in polynomial time. Well, what do you do? But nevertheless, this is also an ongoing work, and that's sort of complicated.
Why is this so? I don't understand what the issue is.
Okay, so
Computing the rank of a matrix is a straightforward.
Computing,
yeah.
But you want to express it in a logical way. So the goal is, like with NP, for instance, any problem a problem belongs to NP if and only if there is a formula in existential second-order logic that expresses exactly this problem. Right? So I want to do the same for the class P. If I can do that, the hope is, well, I have different logics, maybe using my combinatorial skills, I can construct a counterexample that distinguishes these logics, and therefore proving that P doesn't equal NP. But what I need to do, I don't need to compute, I need to express. Right? So, for instance, I want to write a formula that would have, say, 5 models, if and only if the rank of a given matrix is 5. That's exactly the problem. I cannot express in logic way polynomial time computations. That's exactly the issue.
So you want the formula to work only for fixed rank, for constant rank, or?
Well, it doesn't matter. Something. I'd be happy with something. Yes.
You should say, I mean, there is a solution if you use invariantly and auxiliary ordering.
Yeah, well, okay.
So what you try to avoid is the ordering and to...
Yes. So, well, but that would probably deviate us a little too far. So far I'm describing ways I'm not going to follow. So right. Say for hue bicoloring, the logic is unclear at all. So we don't know what we can use here, for example. So this is another way we are not going to follow. Okay. So what else can we do? Well, the way we are going to follow is this. What if I try to separate problems by saying that one cannot be reduced to another by some class of reductions? Reductions. Well, clearly in our case, since we are talking about approximation complexity, reductions have to be approximation preserving. I'm not going to define them here. Well, C. Leslie's and others work for all these definitions, which is pretty standard. And, I'm not going to use it too much, so no definition. What is the specific type of AP reductions I am going to use? As Les teaches us, there are 3 types of reductions between counting problems. Gadget reductions, holographic reductions, and interpolation. Okay, so I'm going to talk about gadget reductions for 3 reasons. First of all, it's number 1 in the list. Well, second, I don't know that much about holographic reductions. And third, interpolation is not approximation preserving. So that's what we are going to talk about. But actually later, if time permits, we will see some kind of funny interplay between these 2 things sometimes. It's maybe a little bit more than just that. Okay, so gadget reductions. What do we normally understand by gadget reductions? Well, we have all these functions and we want to sort of express a function using some gadget. How do we do that? Well, using some other function, of course. So, well, okay, we construct a gadget, right? We use some other function.
Is there a definition of the word gadget?
I will give one.
Okay.
Well, so far it's intuition, what we tend to understand by that. So, well, we have some kind of construction using this old function g, and, well, we distinguish some vertices in this construction as portals or whatever, and we hope that our construction somehow induces what we want on the portals. Right? And then the idea is, if we do everything right, and we are given a problem over this function f. Well, here I assume it's binary, but it doesn't have to be binary, of course. Then instead of every instance of this f, I plug in my gadget, and hopefully this gives me a reduction. Right? So clearly the trick here is to define the gadget in the right way. Okay, so what is the right way of defining the gadget? Well, what I want that I start with a count in CSP, and I end up with a count in CSP, right? In what case I obviously achieve that? Well, I obviously achieve that if my gadget is a count in CSP, right? Then what happens? Instead of every edge here, I plug some kind of more complicated piece, but nevertheless, all in all, well, it remains a count in CSP. So that's basically will be my definition of a gadget. A gadget, in this sense, is just an instance of count in CSP. Well, to be a little bit more precise. So that's what I'm trying to do. Right? So all these vertices here are going to represent variables. Right? We're talking about CSPs. So, well, the portal vertices, well, I will call main variables or free variables, whatever you prefer. And the remaining ones are going to be sort of auxiliary variables. Everything is happening in a certain domain, say D. Okay, then the way I compute my function f using the gadget, well, it's just like that. It's I fix the values of the portals. Right?
What's Z? Z.
Z. Right, I fix the value of the portals and then sum up all the possible extensions to the auxiliary variables. Well, I definitely compute some function, and well, this is what I express using the gadget. Okay, not a small example, a little too early. So clearly, if we are talking about complexity, and if indeed we have this reduction between what we can express and where we started, then for the complexity of the problem, what is important is just what we can express, not where we started. And this sort of motivates this whole notion of functional clones. So what is a functional clone? I start with some small, nice constraint language, say delta, and I construct everything. I take all functions that I can express using gadgets from the previous slide. Anything. Clearly, there will be infinitely many of them. No problem. And the result of that I'm going to call a functional clone. So why clone? Well, historically it was for different types of functions and so on, but the story I've heard, clone is closed set of operations. So C-L-O-N. Okay. Maybe not. Also what E does in the end, I don't know. Or maybe no. Anyway, it doesn't quite work. So I call it a functional clone if the set that includes all functions that can be expressed through functions from delta. Well, for convenience, I will also include all constant functions. We know that for computing partition functions, we can multiply by constants easily. It doesn't cause any problems. And again, for some technical reasons, I will always include this equality function. It's just equality. This is, by the way, what distinguishes CSPs from Holland. So these are kind of important here. Okay, so this is the functional clone. Well, it's very easy to see that if I take some set of functions that belong to the functional clone generated by delta, then the CSP of gamma is AP-reducible to CSP of delta. Very simple. Very simple. So, in a sense, if I care about complexity, I only have to study clones, nothing else. Nothing else. By the way, this is also a reduction for exact counting. Also not the best one for exact counting, but nevertheless. Well, if we think a little deeper about, say, all these small exponential, easy exponential algorithms and so on, then it's also number ETH preserving the reduction. It's because it's so simple, right? We just plug in gadgets. We don't change anything. We don't really change anything. So it's a good one. Okay, small example. Say I start with implication. I want to show an example how we can express things. Say I start with implication that has this operation table. So implication of 0, 0 is 1, implication of 0, 1 is 1, and so on. I take a gadget, something like this, for example. I put as portals, I take these two variables x and y, and I impose implications, well, on those places. So if we compute it carefully, then the function we get this way is this ferromagnetic Ising function, 2, 1, 2, 1, 2. Why is that? For instance, what is the value of the function at 0, 0? I plug 0 here, I plug 0 here. Now, what freedom for those variables do I have? Well, if both are 0, this can be either 0, 1, but this one must be 0. So 2 options. 2. If, say, this one is 0, this one is 1, this must be 1. This one is 1. And this one is 0. So only one option. Okay. Good. Since we care about approximation, sometimes we can take some sort of limits. Okay, so we may use some approximate expression for functions. So by omega clones, now I will call a combination of just functional clone and limits. What do I mean? A function belongs to this omega clone if and only if, well, it can be expressed as a sequence of a limit of sequence of functions, each of which belongs to the functional clone. Right? So I can take limits. Unfortunately, generally speaking, well, limits don't have to behave good with respect to approximation preserving reductions, because constructions for those functions may be very complicated, of course. So if we want to keep reducibility, then we have to restrict ourselves to some kind of efficient limits, say where at every function from the sequence is somehow nicely expressible and so on and so on. Well, in this talk, well, then we have approximation preserving reduction. If we can express something using functional clone and efficient limits, then I have AP reduction between the problems.
Pointwise convergence?
What's that?
What is convergent? What is this limit? Pointwise?
Pointwise, yes. Well, it's finite sets. Right. So for the purpose of this talk, I won't make much distinction between these two. So I will, just for simplicity, I will be talking about this. No efficient stuff, just omega clones. So what I want to do is to identify and somehow study interesting omega clones, interesting in certain sense. Okay, so more precisely, what do I want to do? I have this very large and very small omega clone, and a lot of things in between. So the very large one is the clone of all functions. The very small one is whatever I can get from just equality. Right. I want to know what's in between. It would be nice to draw a picture. It's not quite possible. There are infinitely many of them. We will see it in I don't know. It's very easy to see there are infinitely many of them. So probably a picture isn't that doable. But on the other hand, we don't need the picture. We want some kind of more rough classification. We want to know complexity ultimately. So some interesting parts or important parts or whatever. This is what roughly we want to know. Okay, As I said, I don't have any complete picture or anything, and I have no hope to get one. So what is the rest of the talk is going to be about is some sort of a walk in a zoo of functional clones, of omega clones. Well, as in such a walk, I will try to talk something interesting about every species we will encounter. So okay, a walk in a zoo. Okay, look right. The first animal in our walk is a big one. This is the set of the log supermodular functions. Okay, what is a log supermodular function? Well, a function, I will restrict myself to two functions on 0-1 domain, on 2-element domain. That will be enough. I'm not going to look any further. So a function, say an array function from 0-1 to non-negative real numbers is said to be log supermodular if and only if for any xy it satisfies this inequality. Okay. By LSM, I denote the set of all log supermodular functions. It includes, for instance, implication, ferromagnetic easing, 2-spin of alpha beta where alpha beta is greater than 1. Why is it important, this class? Well, firstly, it includes some interesting functions. Secondly, if you take the log of such function, you get this just supermodular function, which is of course very important for optimization. So the hope is that since it's good in terms of optimization, it may be good in terms of counting as well. Well, it's yet to be seen so far, but nevertheless, there is some hope that we can do a little bit more in this case than just in general case. And of course, in this case as well, it's also we have something in this case. Well, LSM is an omega clone. It's not quite trivial. By the way, well, I will mention various results. Some of them are trivial. Some of them are not. Some of them very non-trivial. But I won't make any distinction between those. So you will never know if it's easier or difficult to prove. So this one is not very difficult, but it's not trivial. Okay. So another reason why LSM is important. If you look at the conservative clones, and again, we have heard about conservative problems in this workshop already, that is those clones that contain all unary functions. All unary functions. Not every clone contains all unary functions, but let's look at those that do. Then, one can show that all clones with this condition are either between imp and LSM, this is implication, and LSM, or they are shown in the following picture. So it's the clone of all functions, well, LSM of course, okay, there is a connection between them, imp, well, there is something between them which is not shown in this picture because we don't know what's in between. There is this affine function which corresponds to solving linear equations. And there is equality. And there is nothing else somehow. So this is all. If we have all unary functions, then we know everything. We can classify the complexity of everything except for this part. And even about this part, we know that this is BIS equivalent. What about this? I don't know. Okay. If there is anything and how much is in between imp and LSM, well, again, we don't know. Also, I will return to that a little later. Yeah.
For LSM, you know counting is doable, or you don't know?
We don't know. It may be number sat hard. It may be BIS hard. It may be BIS easy. We don't know.
LSM with some conditions gives you FKT, right? FKT inequality. Doesn't that help you count? No,
I don't think so. No. It seems nothing helps. Okay. Okay. What else? Well, LSM functions help in more general cases. Say one of the most general classification results. Obtained by probably 70% of this room, is this. If I take a conservative in the same sense, containing all the unary functions on a finite set D, then any count in CSP is either f-pressable or number sat hard, or in AP introducible with a clone between imp and LSM. Right? It's not clear what's between them. So if we know, well, we could complete this classification. So a good chunk of the goal of this workshop would be completed. So yes, LSM are important. Okay. I don't know, we don't need to know what Fourier coefficients are. I just need some piece of terminology for that. Well, for a function, I can compute the Fourier transform of this function. And, well, Fourier transform is a function itself. Right? It's also an array. Well, its values are also real, also don't have to be non-negative. Even if you start with a non-negative function. Okay. I call a specific value of this Fourier transform an even Fourier coefficient if the Hamming weight, the number of ones in this value is even. Well, I call it odd if the Hamming weight is odd. Well, I will need these two things somehow. Okay. Clones that are given by odd Fourier coefficients. Okay. Let's take all functions whose Fourier coefficients are non-negative. Oh, why not? Or let's take those whose even Fourier coefficients are non-negative, but odd ones are non-positive. Well, two sets of functions. Why are they interesting? Well, again, they contain some interesting cases. Say PF contains imp. Anti-Fraser. And this 2-spin in this interesting case, which is slightly weaker condition than alpha times beta is greater than 1. Okay. They are omega clones, which is good. And we know a little bit about them. Say if you take binary functions from PF, then there is an f-press for them. Well, for instance, this gives immediately that 2-spin of alpha beta in this case is f-pressable. Well, it's unpublished, is it? It is not.
Yeah, he's gone into history.
Okay, so this explains this question mark here. So Colin proved it but didn't publish somehow. Okay. Now look left. Self-dual functions. Well, I say that a function is self-dual if for any assignment f of the assignment, and if I flip every 0 and 1 in the assignment, the value is the same. Again, if you look at what people are doing, well, in this workshop in particular, most of talks are concerned with self-dual functions. Right? Okay. SD is the set of self-dual functions, and well, it includes all Ising called 2-spin alpha beta and many other interesting things. Well, it's somehow related to odd Fourier coefficients, say odd Fourier coefficients of functions from SD equal to 0. Sorry. How can we use self-dual functions? Again, we don't know much about that. Well, for instance, it's very difficult to get results even about these classes, and these are only small part of SD. But nevertheless, of course, SD itself is hard, but maybe some fragments of it may be interesting. Well, there is a kind of interesting use of those self-dual functions. So, first of all, it's in some sense, well, it's an omega clone. In some sense, it's very big. It's maximal. If you add any function to SD, which is not SD itself, then you get all functions. You can express any function at all. So it's very big. On the other hand, it's very small. Because it's generated by any anti-Fraser function. So it's somehow very special, in a sense. Somehow very special. But it also helps to prove various things. Well, for instance, let's look at this trick that I call dualization here. Say we have this set lattice of all clones, okay, and I take this interval which starts at SD and, well, everything between SD and equality. What I can do, I can convert any function to a self-dual one. Just multiplying by this, flipping all variables and multiplying them. Clearly, this one is self-dual. What does it mean? In terms of this picture, it means that I map all, well, the clone of all functions using that into the clone of self-dual functions. And the clones of equalities, okay, well, they remain the same. Okay, fine. If I take imp and LSM, well, it's easy to see that I apply the same thing to LSM, for instance. I get again the whole clone of self-dual functions. If I apply imp, well, I again just get this equality, nothing else. Now, there is an interesting clone here. Self-dual with positive Fourier coefficients. Again, it's maximal here, so this is a simple interval. There is nothing in between. Let's take its preimage. What is it? Well, it turns out it's something known. So this is the only known clone so far between imp and LSM. And you can construct it this way. Somehow. Well, maybe if you know more from here, maybe you can construct more there. I don't know. But we don't know much about what's below SD. Okay. Not class. Something expressible by match gates. Let M denote the set of all functions. What's that?
What is the animal?
It's one of the dinosaurs from Jurassic Park.
Okay.
The one which spits some, I don't know, acid or something like that.
So the class is extinct too?
No, well, it's resurrected, right? Like the dinosaur. Okay. So let's let M denote the class of all function whose Fourier transform is expressible as a match gate with positive weights. Again, it's something that has been looked at. Also, I wouldn't say it was thoroughly studied. Also, some variations of this class are very thoroughly studied. For instance, those that are expressed by planar match gates with possibly negative coefficients. Well, we know a lot about this one. Say, it includes functions that satisfy certain identities and so on, for example. Well, another similar thing that, well, we may be interested in the class of functions that, for whom the Fourier transform is expressible by planar match gates, but using only positive weights. Well, M includes some kind of interesting functions. For instance, this Fourier symmetric function with this signature. So the value depends only on the Hamming weight. If Hamming weight is 0, then it's 5. If it's Hamming weight is 1, it's 1, and so on. So it does include some interesting functions. This one and this one are functional clones, which is again kind of an odd thing if you think about it, because we are imposing conditions on the Fourier transform. But since we know so much about, but we don't know if it's an omega clone. We don't know what happens if we take limits. But since MP is given by identities, well, okay, we know that it is an omega clone. Okay, it's time to draw some pictures, perhaps, just to classify things we know so far. Again, we start with something big, with something small. There is this thread between EQ and all functions related to LSM. We have this positive odd Fourier, negative odd Fourier, self-dual, which is the same as Ising. Well, we have an interesting intersection, which is just below SD. Well, we have this clone generated by M and MP. It should probably be here, not quite here. I'm not sure about this connection, if it should be here or here, by the way. And the intersection. So that's what we have so far. Okay. I have two more animals. Probably we can look at one of them and then I show the final picture. Fraser. Small. Well, first of all, we know that Fraser is can be reduced in the holographic sense to the counting of even subgraphs. But actually, it turns out that they also generate the same clone. So somehow holographic reduction here, Gadget reduction is the same. So you can work hard or do nothing, but you get the same result. It tells you something about it. It's really tiny. It's really tiny. It's below imp as we know now. So it's very, very low here. Okay. And now the final picture. All right. The final picture is this. So, well, this is what I've shown so far. Well, I also have this clone of monotone functions and various variations of monotone functions like this that are parameterized by a non-negative real number. And for each non-negative real number, you have a separate clone. So this thick line means that it's well. I just make all the continuum points here. Right, so this is how they... Okay, I probably won't be talking about the list of open problems, since we have this uncountable lattice, we have uncountably many problems, and so I couldn't make a list. But, okay. Don't look here. Okay, thank you.
For this M class, why do you look at the Fourier transformation? Like after Fourier, you get a match gate. Right? Why do this?
Why do we do that? Yes, exactly.
You just tested me there.
No, I forgot. Why we don't do that? So it's a kind of strange coincidence that after Fourier, it forms a clone.
Other questions?
In some other similar context, you have this Galois connection, and you have this the function. You have the clone, and you have this alternative object. And do you have something like that for this relation?
No. So if you look at my tutorial at the bootcamp, well, I discussed that in substantial details.
More questions? Okay, so let us thank the speaker again.